Okay, I hope you remember that we've already had an introduction to linear approximation. So if you don't recall, read these notes first of the plan. So the idea is to use a tangent line approximation whenever you don't want to do the calculation of a point on a curve. So first we did a square root function. So let's graph f of x is the square root of x. And I'm going to exaggerate my graph here. It's really a slow rising graph, so I don't really have this drawn to scale very well. And the idea here is that I don't know what the square root of 9.1 is, but I do know the square root of 9, which is nearby. So I find an easy point in the neighborhood, and then I find the equation of the tangent line at that easy point. So then, once I have the equation of the tangent line, then I can put 9.1 into the tangent line equation. That's a much easier calculation. Once I find the y-coordinate on the tangent line, I can see that that's going to be a pretty close approximation for the red point's a pretty close approximation of the blue point, especially considering how I've exaggerated my graph. And it's very easy for us at this point, I hope, to find the equation of a tangent line. So its slope comes from the derivative of the function, and we're going to use the point 9, 3 as our point of tangency. So I simply need the derivative when x is 9, and we'll get 1/6. So our tangent line has the equation y minus 9, x coordinate, y minus 3 is equal to 1/6 x minus 9. And then all we need to do to find that red point is substitute x equals 9.1 into our tangent line to find the y-coordinate. So y minus 3 is equal to 1/6, and that parenthesis would be 9.1 minus 9. 0.1, since I have this 1/6 as a fraction, I'm going to write the 0.1 as 1/10, and that would be a 1/60th, and then we move the 3 to the other side. So 3 and 1/60th is our approximation. So what you just found out, this red point is at 3 and 1/60th. So it really isn't the blue point that we're looking for. So to clarify what we've just found, so in order to avoid doing the square root of 9.1, I'm approximating it with the red point on the tangent line. So the y-coordinate of the tangent line is a nice approximation. And then remember, because our function was concave down, visually it's very easy to see why our approximation is an overestimate. So this is an overestimate because our function was concave down. Since f is concave down. So remember, tangent lines are above the function when it's concave down, and tangent lines are below the function when it's concave up. And you'll see that here in our next example. And in our next example, we're going to raise 2.001 to the 5th power. Well, I'm not so fond of doing 2.001 times 2.001 times 2.001 if I had to do that arithmetic by hand. But if I think of the function y equals x to the 5th, I certainly know that 2 to the 5th power is 32, and that's going to be very close to the point that we're approximating. All right, so I should clarify here that the x to the 5th graph is really going to rise very quickly. So I've made my graph exaggerated, the curve here, because otherwise it's almost too close an approximation to get a good picture of it. So the point here is that we know 232 lies on our function, but we don't know the y-coordinate at 2.001. But if I find the blue tangent line, if I find the equation of the blue tangent line, then it's not so bad to put 2.001 into the tangent. So our y-coordinate of the blue point on the tangent is our approximation for the actual red point on the graph. Okay, so what do we need to find the equation of the tangent line? We need to know our slope. So the derivative of y is 5x to the fourth. And now we do our easy point. So the derivative when x is 2 would be 5 times 2 to the fourth. 5 times 16 is 80 for our slope and our point of tangency. So now we know our tangent equation, y minus 32 is equal to slope of 80, the derivative, times x minus 2. And now to find that blue point, we're just going to substitute x equals 2.001. So we're going to put that in and we'll have 1,000th in that parenthesis. So y minus 32 is equal to 80 times 0.001 if you prefer. I'm going to write it as a fraction just to remind you. Decimals or fractions. So here we'd have 8 over 100. So y minus 32 is equal to 8 over 100. I guess I could divide by 4. So we would have 2 over 25. Or we could do that in decimal form. Let me finish this. 32 and 2/25. Maybe you left that in decimal form. Y minus 32 is equal to 80 times 0.001. So I'm not sure why I did fractions, just habit, I guess. So when I multiply here, I will have 0.08. So does it matter whether you give your approximation as a fraction or as a decimal? Not a bit. So what we've just found is that 2.001 to the fifth is not exactly these values. Remember, we just found, let me clarify here in our picture, we just found the blue point right here. So we just found this coordinate is 32.08. The blue point on the tangent line, but it's serving as our approximation of the red point. So the red point is approximately 32.08 or 32 and 2/25. All right, differentials. Each piece of the dy dx can be called a differential. So if we start with the equation y equals x squared and we take its derivative with respect to x, dy dx is equal to 2x, then just like working with proportions in grade school, we may move the change in y, the derivative, the dy stands for the change in y, and the dx, the change in the x. So we may split those in some problems. So each of these written separately is a differential. So a derivative is made up of two differentials. All right, so we'll use that in some problems. Sketch tangent lines at each point. So this we've talked about already. Sketch tangent lines and can you discover when the tangent line will be above the graph? When it's concave up, the tangent lines appear to be above the graph. Oops, sorry, I said concave up, and that's exactly concave down. When it's concave up, the tangent lines are below. And here we've got some of each. Here's an inflection point. So notice in the concave up section, the tangent stayed below. When it switches to concave down, the tangent moves above. So again, something you don't have to memorize since you can recreate that. So the tangent line is below the curve. The tangent line is below when the curve is concave up, and above when the curve is concave down. So as we've seen with our overestimates and underestimates, if we found a point on this tangent line, it would be higher than the curve itself. And if we found a point on this tangent line, it would be below the actual point. So our linear approximations will be overestimates. It will be an overestimate in any concave down interval. And it will be an underestimate in any concave up interval. All right. So let's try our linear approximations again. So we've got to think of what function we're going to use here. So this looks like we should use an e to the x function. And you know what an e to the x graph looks like. It has a horizontal asymptote of y equals 0, has a key point of 0, 1, and we're looking for a place very close to that. So in fact, let me move my 0, 1 here. We're looking for the place where the x coordinate, if we use the e to the x graph, we're looking for the place where the exponent is negative 0.015. So we're looking for a point, and I'm exaggerating the distance here, it would really be very, very close to that 0, 1 point. So that 0, 1 point is where I'm going to draw my tangent line, and I'm cheating a little bit here to make it visibly different than the blue graph. So we're going to use the red point on this tangent line. So our point of tangency is going to be 0, 1. It's very close to the value we want. So x is very close to our desired x value. So the slope is going to come from the derivative. So f prime of e to the x is still e to the x. So f prime of 0 is e to the 0, which of course is 1. So we get a nice, that red tangent line has a nice easy equation. Y minus 1 is equal to the slope 1 times x minus 0. And now what we want to do is substitute in our desired point. So now we're going to substitute into the tangent line. We don't really want that. We really wanted the blue point on the e to the x curve, but the red point on the tangent line will serve our purposes. So we're going to substitute negative 0.015 in for x. So we'll have y minus 1 is equal to negative 0.015, and we'll add 1 to both sides. Not so difficult if you're careful with your arithmetic. So what will we come up with? A positive. We're adding 1 to both sides. So a 0.985 is our estimate. So we have that our blue graph, e to the negative 0.015 power, is approximately the same as this coordinate is on our red graph, 0.985. And we can look at our graph and see that the e to the x curve is concave up, so we would know this is an underestimate. This is an underestimate since e to the x is concave upward. Okay, but pretty simple to do. All right, now we want to do the 2/3 power. So let's think. Our function is always pretty obvious. Our function we want to use is x to the 2/3, or you could write it as cube root of x squared if you prefer. So notice that this is an even function. So you should know what the cube root graph looks like. Let me just sketch it and erase it. Here's our cube root graph, right? So when we square x first, our x's would be a little bit bigger, and they would all be positive. So squaring the x first is going to give us a symmetrical graph. So it's going to look like a seagull. So hopefully that will all make sense. And what are we interested in on the seagull? We're interested in, I'm going to draw that more with a curve here, we're interested in just the right wing of that seagull. And again, it's kind of a slow riser, but I'm going to cheat a little bit. So we're interested in the place where the x-coordinate is 8.06. And I definitely do not know the cube root of that number squared. But right next door to it, if I do 8, I can do the cube root of 64, or I could do it in the other order. Remember, might be worth pointing out here, would be logical to do the cube root first and then square it. Those are all equal. So I do know that the cube root of 8 is 2 and then square it is 4. Or you can do the other order, square it first to be 64, and its cube root would be 4. So there's our easy point. And then let's draw the tangent line there. And I might not even be making these straight because I'm trying to give us enough space. So you can see that the point on the tangent line is a little bit above the point on the actual curve. So I'm going to put 8.06 into the tangent line function. So I know f prime of x by the power rule is 2/3 x to the negative 1/3. And I want to find that at our easy point of 8. So this is really 2/3 cube root of 8. So we would come up with 2/3 times 2. So we'd come up with 1/3 as our slope. So our tangent line, our blue tangent line in our picture, has the equation y minus 4 is equal to 1/3 x minus 8. And then to approximate our blue point, our red point rather, we're going to substitute 8.06. So let x be equal to 8.06. So y minus 4. And again, your choice here, 1/3 is a repeating decimal, so I would choose to keep fractions here. So 8.06 minus 8 is 0.06, but I think I might write that as 6/100. And of course, right away, 6/100, you could reduce that to 3/50. So otherwise, you can cancel here and then cancel. So we're going to come up with 1/50th, or now if you prefer either way, once you see that, we know what that is as a decimal, 0.02. So whether you give the answer as 4.02 or 4 1/50th, remember that that is the blue point here. 4.02 is not actually the red point we're looking for, but we're saying that it's a close approximation. So I keep repeating that, hopefully that you will see that 8.06 to the 2/3 power is only approximately equal to this point on the blue tangent line. Okay? And again, we can see that our graph in this section is concave down, so this is an overestimate. Since f of x is concave down. And I think that will do it.